Uh, Decided to see if there was any interest in continuing this monthly webinar series. So I put together three webinars. This is the first one of the series. There'll be more if I see that there's enough audience interest in this after hours sort of way of learning about heliophysics and interesting topics. So to select this topic, I decided that, I'm going to use the information that I have from my Astronomy Cafe website. And it turns out the most popular question and blog always is the Earth's magnetic field about to flip? That question and that blog just simply gets beat up every time I put anything up there on the subject. So I said, oh, okay, well, that's related to heliophysics, Earth's magnetic field. So let's put a webinar together and see if it meets the needs of the audiences that I seem to attract. So just as a background, we can think of NASA doing research in heliophysics, and it kind of grouped roughly around three big topics: what causes the sun to vary, how do the Earth and the heliosphere respond, and what are the impacts on humanity? These are called the three big questions for the heliophysics area. There are similar ones for astrophysics and planetary and Earth. And Hillary, Christina Millot, and myself as an advisor sort of have been working on this framework for heliophysics education, which shows how these big questions and their subsidiary questions can be mapped into the national science standards, the next generation science standards. So as a preamble to this is where we are in terms of these subsidiary questions. Tonight's talk is going to be 2.1, meeting the subsidiary question 2.1, which is the closest matched I could find. And then you see in parentheses at the end, you see the the next generation science standards, attributes that are met by that particular question. So, okay, here we go. Let's get in the car and drive. Is the Earth's polarity, is its magnetic field about to flip? This has been a perennial question that people ask me a lot of the times when I give talks on various topics in heliophysics. They just sort of raise their hand and say, oh, enjoyed your talk, but isn't the Earth's field about to flip? And they can ask this question in the middle of a talk on sunspots. So it's an interesting question. To answer it, or to at least frame an answer, first we have to figure out what the called the geomagnetic field, the Earth's magnetic field, what it looks like, how it's produced, and how it's changing in time. This is analogous to, if your car breaks down, you need to understand how the engine works to know whether or not this is going to be a simple fix, to get your wrench out, or if it's going to require a major engine overhaul. So to answer the question, we have to really understand what it is, how it's produced, and how it changes. So my question to you, this is part of my audience participation part. Question to you, what do you think the inside of the Earth looks like in terms of the magnetic field? Think about this for a few seconds or a minute. And go over in your mind sort of these visual clues and things that you've seen in textbooks, maybe sketches that you've seen about what a cross section of the Earth looks like. Maybe you've seen a drawing in Scientific American or some other media source. So that's what we have to work with. But now the question is, which of those visuals that you're using to represent the Earth's magnetic field comes the closest to what we understand that it looks like? Now, there's the problem, because here is a typical textbook illustration. This comes out of the Earth Science textbook from McGraw-Hill, the 2017 edition, and this is likely the kind of a thing that you'll see. You'll see something that resembles a bar magnet stuck inside the Earth, and then you'll see these loopy lines coming out that resemble the magnetic, the iron filings on a magnetic field that you see, or that you create, in a student lab. As a comment here, they have the north and the south reversed in this figure. So already the figure is an error, even as it is a simple illustration. Now, so it's wrong. It's a wrong image that you have of what it looks like. Now let's take a look at progression over time. Here's what a Principles of Physics textbook looked like in 1895. Here it shows an actual bar magnet sitting inside the Earth, and it has its south-type pole in the northern hemisphere and its north-type polarity in the southern hemisphere. The polarities are accurate in this case. It's an interesting thing that when you have your compass and you're trying to navigate with your compass, the compass is pointed and it has a little N on it, or sometimes it's colored red. So you follow that direction in the northern hemisphere and it'll take you close to the north rotational pole of the Earth. That's why it's labeled N, because that's the direction to the North Pole. But if you think about it, that's the convention that's used to identify polarity on a magnet. You have the N on one end of the magnet and the S on the other. The problem is that north repels north and south repels south, and only south attracts north. So that means that all of these magnets that you use in your compasses in the northern hemisphere that have their N pointing to the geographic North Pole, the north magnetic pole is a south type pole. That's why it's attracting the north type part of the magnet that you have that you use in your compass. And this convention is used over and over again. If you take a toy magnet and it has N on one side and S on the other, and you compare it to the compass, they line up perfectly. And if you have an unknown magnet, you can figure out what the polarity of that magnet is just by comparing it with the compass needle and the other magnet. So it's a completely consistent historical convention that we use for identifying polarity in magnets, pardon me. But the problem is that the interior of the Earth is not a simple bar magnet. We've known that for a fairly long time. The polarity is not north type, just because the compass needles point north, as I just said, even though you're going to see some figures that look just like this. They have a bar magnet in the interior of the Earth, and they have its north polarity in the northern hemisphere. Completely wrong. They don't even get the cartoon correct. Here is another thing. The field does not originate near the surface of the Earth. Some cartoons like to have the bar magnet going right up to the surface of the Earth and touching it at the Arctic and Antarctic. No, doesn't look like that at all. If you want to be sophisticated and say, oh, if I have a loop of wire and I put a current through it, I'm going to get a magnetic field. If it's a solenoidal sort of coil like this, it's going to have a north and a south end. So maybe that's what the interior of the Earth looks like. Maybe there's a current flowing in the interior of the Earth that makes this north and south magnetic field. But that's not right either. The interior of the Earth, neither is it a bar magnet, nor is it an electromagnet that can be represented in this way. So to improve on this representation, all of a sudden we've thrown out just about everything that you know about the interior of the Earth's and its magnetic field, how you should sketch it, what it would look like. So now we have to say, okay, well, what are some other basic properties we know about the Earth? Maybe we could use those properties as a clue to figuring out how the magnetic field is generated. Okay, so I'm going to give you a short few moments to sort of dwell upon this before I go on to the next slide.
Stan, would you like people to chat in the chat and
Absolutely.
offer some of the basic properties that they think should be considered?
Absolutely.
So if you all don't please take a moment. And I guess my question, Stan, is like, why are the images so wrong? Like, why do we seem to perpetuate these misconceptions with images that seem to be wrong?
Right, because they're useful cartoons. The effective magnetic field outside the Earth looks as though it's produced by a bar magnet inside the Earth. But geophysically, there is no way to have a bar magnet inside the Earth. We know that the Earth has a variety of layers that change in density and temperature. We know that the inner core is solid, surrounded by an outer liquid iron nickel core that's kind of like a sluggish fluid. So there's no way that you can construct a bar magnet kind of magnetic field out of that mess. There's also no way that you can create a singular current that produces a flow of current in the interior of the Earth that would produce a magnetic field like this. It's got to be something more complicated. Okay.
So we've simplified to the point of making it wrong.
We have simplified the interior model of the magnetic field to the point of making it incorrect compared to the last 20 years worth of research. Okay.
Okay, thank you.
But you'll see this even in textbooks in 2017, like I showed you at the top of the hour. It's a useful conceptual model. And since magnetic fields of the Earth are not covered for the most part, no harm, no foul. You teach the kids this, the kind of cartoon, and no problem. They can still navigate around on the surface of the Earth using a compass, either using the correct model or the incorrect model for the interior. At the surface of the Earth, both models become very much equivalent to each other, but only one of them is technically accurate in light of current research. And that's the point of this talk. Okay, so what kinds of things did you come up with as additional properties of the Earth? Just one or two examples.
You guys can unmute yourselves if you'd like to say yourself, or I can read them from the chat.
Okay.
There's an interior temperature gradient, Michael says.
Yes.
Joanne says high temperatures and heavy movement and rotation.
Yes.
Kelly says the basic properties are being made of nickel, iron in the core, and there are several other elements in the layers. The outer core is liquid metal.
Yes, absolutely.
And the
Good.
pressure.
This is, I'm sorry.
This is a sharp group, see? Michael says the pressure increases in depth.
Yep. This is better than I hoped. Okay, and so let's now take a look at a better model for the interior of the Earth and how magnetic fields can be produced there. Earth rotates. Yay! All of you got that one. The Earth rotates. Wow, a miracle. So we got to use that as part of our toolbox for building the interior of the Earth. It's a rotating system. Now, what happens with rotating systems that have an atmosphere or a low density medium above them? Well, there's something called the Coriolis force. All rotating things that have stuff moving around on their surface, that material experiences what's called the Coriolis force. I'm not going to go into the details, but it basically produces, on the surface of the Earth in the atmosphere, produces tornadoes, hurricanes, things like that. So that's property number two that's of interest. Because now think about it. What we have in the interior of the Earth is a region which is a molten iron liquid, iron nickel, in the outer core. We have a rotating material, so that material which is conducting is rotating around the axis of the Earth. And surely, because it's a rotating fluid, it's going to be experiencing Coriolis forces, which means that in some way, there are going to be cyclones or tornadoes in this iron nickel material. Well, that's really cool, because here's what we can do with that. The Coriolis forces produce rotating columns of currents in the Earth's conducting outer core. So that little ribbon that you see there going up and down, that's caused by the Coriolis forces in the outer core of the rotating inner Earth. Okay. So now it's interesting because that outer core is a conducting material and it can support electric currents. Now, all of a sudden, with this cyclonic sort of Coriolis force hurricane kind of a thing going on there, you can have rotating currents that are roughly parallel to the axis of the Earth's rotation. Now, if you think about how an electromagnet works, you've got a coil of wire and you put a current through it, and it produces inside that coil, it produces a magnetic field with a certain orientation, north and south, depending on the direction of the current flow. Well, You've got a very similar thing going on within these columns that are produced by the Coriolis effect in the outer core. So, very cool. Each column generates its own bar magnet field. Okay, that sort of is a self-explanatory comment. These individual fields merge together in the outer mantle, and the net result is at the surface and beyond, you have what looks like a bar magnet bipolar magnetic field. All right. But now what you've done is you've replaced the bar magnet clunky 150-year-old model with a more interesting physics-based model, which shows that the outer core has some really cool, interesting things going on. What is also interesting about this system, it's called a magnetic dynamo. That means that it's a self-exciting system, that the magnetism is produced by the current flows, which then enhance the magnetic field, and that feeds back on itself. And so you wind up with a magnetic field that's extremely strong and robust. However, there's another system that has a conducting material at high temperature that also has a magnetic field, and that's called the sun. The sun's magnetic field is produced by a dynamo process too. However, that process reverses itself every 11 years. So that's why you have sunspot cycles. And so your question might be, well, if we're going to say that a magnetic dynamo is producing the Earth's magnetic field, does the Earth's magnetic field also have an 11-year reversal cycle? No, because it's iron nickel in an almost solid state, whereas the sun, it's a plasma, which is a very mobile fluid on the sun for the most part. So the dynamo on the sun is going to change very quickly every 11 years, but for the Earth, it's going to be much, much more sluggish. Okay, so that's the big difference between the two systems, even though the mechanism seems to be the same between the two in terms of how the magnetic field is actually produced. If you were to measure the Earth's magnetic field at the surface, you would see the blue shows that it's a south-type magnetic polarity, and the southern hemisphere, it's a north-type magnetic polarity. But you notice there are little squiggles and loops here and there. It's not a uniform, smooth, hemispheric distribution of magnetic field. In fact, if you subtracted off the main part of Earth's field and only looked at the residual, you would get something that looks like this. This is a 1 part in 1,000 variation in that main field, but you can see that there are big blobs here and there. You see that, for instance, there's seemingly north-type magnetic field polarity variations down in the southern hemisphere, and in the southern hemisphere, in that red blob, you also have south-type magnetic polarity, but then you see a little bit up there in the northern hemisphere as well. So at this level, the Earth's magnetic field is kind of lumpy. It's not uniform. And the very interesting thing is that those lumps move around and change over geologic eras. They move around, and when a lot of them cluster together in one hemisphere, that becomes the polarity of that hemisphere. Here's a case of taking a supercomputer and throwing physics equations at it to simulate this magnetic dynamo in the Earth. And it does a fair representation of creating Earth's magnetic field. And you see that, and this inner part there is basically the outer core zone where the field is being generated. And it's a fairly low resolution, so you can't really resolve the individual columns. But you get an idea that it's very lumpy looking. It's not smooth like a bar magnet magnetic field. The generating region is actually quite lumpy. And those lumps change in time and merge together. And ultimately, what you wind up with, you can have on the far left a nice south-north polarity, which is what we have now. But then during a transition, you have a mixture of polarities going on. And then finally, after the reversal, you'll have a north-south polarity as the stable final state. All magnetic dynamos go through this instability process because it has to do with fluid and plasma flows, which are not stable in time or in space. So that's the reason why we have reversals and changes in the Earth's strength and things like that. Here's another view of this reversal process. In the far left, we have a north geographic pole and south geographic pole, but we have a south polarity in the north and a north polarity in the south. During the transition, you can see these blobs start to form and migrate around and loop around. And then finally, in the far right, we have the opposite polarity appearing in each of the hemispheres. So that's kind of the way the reversal happens. It's not like a bar magnet rotating around 180 degrees, which is what you would get if you used the wrong picture. It's more like mush in a boiling pot of water where each of the convection cells was either blue or red, and you sort of watch this bubbling, boiling sort of action going on, which can sometimes get together to form big cells that have one type of polarity, and sometimes it's all fragmented. Depends on where you are in the cycle. So what we do know today is that the Earth's magnetic field is weakening. We've known that for at least a century now. And for a lot of people, that's kind of troubling because, oh my God, if the magnetic field of the Earth is weakening, what is that going to mean for animal life? What's it going to mean for all these other things? And is it going to weaken to the point where basically it goes to zero and then flips over and starts growing in an opposite polarity? Well, that's the big question that we're going to look at tonight. So the question is, are we headed for a reversal? I'm not quite sure how to do a voting like this, but maybe we could sort of try to figure out how many of you think we're headed for a reversal and how many of you think that we're not. Just looking at this trend, which I've shown here with the gold arrow.
You can put yes or no in the chat. Sten, I was also just asking, we've got all sorts of content areas represented. We have earth science teachers and algebra and 7th grade math. We have chemistry, physics. So they're looking at this from lots of different perspectives too.
Right.
We have a bunch of yeses and we have a no.
Okay.
Yes, but not in our lifetime.
Mm-hmm. There's two of those and 3-4 no's, maybe.
Okay. All right. I think the answer is you're all right. All of you are correct. We are headed for reversal, but maybe not for a while, and it may not be the next one that comes up that's going to be the big one. It's just like waiting for the California earthquake. Yeah, we're going to have a lot of little ones, and it might be a long time, or it might be tomorrow that we have the big one. Okay, so let's take a look at this problem. Predicting when something is going to happen, in this case, this is a plot of the strength of the Earth's magnetic field, its entire strength, plotted year by year in the units called a moment, a magnetic moment. Don't worry about what the units are. They're ampere meters squared. All right. So what we do, if we try to create a trend line, is we use a linear equation of the form y equals mx plus b, where m is the slope. And so in this case, we calculate the slope from the information given. We have the year 2000 value is 7.8 by 10 to the 22. The 1950 value is 8.45 by 10 to the 22. To get the slope, we difference those two numbers and divide by the elapsed years between the two. And we get a slope of negative 0.0043. So the slope is negative, which means that the magnetic field intensity is decreasing in time over this interval. And the final linear equation looks like the one I have down below. Y equals slope times t minus 1850, because we started our time zero at the year 1850, and then we add the constant term, 8.45. So what do we get as a prediction for when y, the magnetic moment, goes to zero? Well, y equals zero in the year 3815 of the current era. So we have to wait another 1,815 years from the year 2000 before this linear trend says that we're going to go to zero in terms of magnetic field strength. Well, 1,815 years from now, I'm not planning on being around, but who knows? You know, I could be the first human that survives for another 1,800 years. I'm feeling pretty good. Who knows? But the thing is, it's a bit more complicated than that. And, you know, everything is a bit more complicated than that. I mean, that's the nature of the world we live in. I mean, you can approximate it in a simple way, but then you have to tweak it. You know, if you look in more and more detail, you have more and more data, and you discover more and more things that have changed your simple model into something a little bit more complicated. And so the goal of science research is to sort of keep up building better and better models that are physics-based, that keep up with the type of data that we now have available to ourselves. So anyway, here is the last roughly million years of the Earth's magnetic field strength. In that plot, you see it goes up and down like a zigzag kind of strange mountainous terrain. And what we now have to understand is that there are two kinds of major changes to the Earth's field. There are things called excursions. Those are things that I've circled there with the black circles. Those are situations where the field suddenly makes a precipitous decline in strength, but then recovers. It might decline by only maybe 10%, or it might decline by 50%, but then it recovers back up, and then the pattern starts again. Reversals, however, are the most extreme of these excursions. In that case, the strength of the magnetic field goes almost to zero. The only thing left over is the remnant magnetic field that's frozen into the rocks at the surface of the Earth. And that's roughly about 5% of the total strength of the Earth's magnetic field at the surface. So once you get down to that red line, you're now in a regime where the magnetic dynamo has stopped producing a magnetic field. For whatever reason, it's a chaotic process, but that's where you wind up with the field going to zero and then recovering. And when it recovers in the opposite polarity state from where it was before. The Brunhes-Matayuma reversal is the most recent one that we've had. It was about 800,000 years ago. There have been plenty more over the last 10 to 50 million years that we've been able to track. These really big changes that lead to reversals, magnetic reversals, the period is anywhere between 500,000 to 1 million years. So it's hard to say whether we're going to have one soon or not for another 100,000 years. It's not a periodic process. It's not cyclical like the sunspot, numbers in a solar cycle. It's its own thing. All right, so here we have excursions are changes in the Earth's magnetic field strength. We have reversals, which are excursions that reach the extreme limit of zero, roughly zero field strength at the surface. So you can say that all reversals are excursions, but not all excursions are reversals. All right. It took me a long time to come up with that. I guess it's called a syllogism or something, but it's true, and here's the thing. We have to figure out our little change that we're talking about is that red circle there. About 10,000 to 15,000 years ago, Earth's magnetic field was almost twice as strong as it is now. Okay. But if you go back 40,000 years, the Earth's field was even weaker than it is now during what's called the Lescamp excursion. This is based on data that comes from this geographic region. They were able to carefully measure the fossil magnetic field of the Earth at that time, about 42,000 years ago, and they found that it was only a couple of these Vadim units in strength. So 10,000 years ago, it climbed up to 11, and now it's back down to about 7. And so we're definitely going through an excursion now. We're sort of halfway down to the bottom red line, but we don't know if that's going to be a reversal ultimately, or if it's just going to bounce back up, like a ball on a tennis court. We don't know when it's going to bounce back up if it does. So here we can start talking about the odds that the change that we're seeing, the decline that we're seeing now, is going to simply be a reversal or an excursion, which means that at some point in the future, it's going to rebound and start growing back up again without changing the polarity of the Earth's magnetic field, or it's going to be an excursion, which means it's going to continue to go down, down, down to zero in another 1,815 years, at which point we'll have a full-blown magnetic reversal. We can work out the probability of these two just by looking at the past record. And we notice there are far more of these excursion events than there are reversal events. There's only one reversal event in the last 800,000 years. But there are 16 of these magnetic excursions. So now we can kind of come up with some odds. There are 17 total excursions, one of which was a reversal. So the odds are 1 in 17 that the current event is going to lead to a reversal. But there are 16 excursion events that didn't lead to a reversal at all. So those odds are 16 out of 17, or 16 and 17. So just by looking at the odds, the current decline that we're seeing right now seems to be far more likely that it's just going to be another excursion than it's going to be a full-bore magnetic reversal. Okay. And so that's basically what we have here. It's probably statistically, it's about 16 times more likely that the current decline that we're seeing is simply going to be an excursion than it would be a full-bore magnetic reversal. In either case, something between now and 1,815 years in the future is either going to show that it's going to be reversed with a new polarity, or it's just simply going to grow back up in the current polarity and no harm, no foul. Whales will continue to navigate like they always did. The sun will rise in the morning and there'll be no real harm. Now, the question might also be that comes up, and I see this a lot too, is that, well, if the polarity of the Earth's magnetic field flips, that means the rotation axis of the Earth is also going to flip. So somehow the Earth is going to start rotating backwards during this reversal. I'm going to show you that absolutely is not what's going to happen. And we can do this, requires a little bit. Oh my gosh. I let the cat out of the bag. That was supposed to be an open query to the audience to vote whether they thought the Earth's magnetic field was going to flip and the rotation axis was going to flip too, or if the rotation axis was just going to stay put. Well, anyway, I mean, you can look at this and you can sort of vote mentally what you thought the answer to that would have been. And I suggest from this audience, given where you are, you probably would have thought, no, the Earth's rotation axis is going to stay put and the Earth's field might flip around or do anything, that it wants, but that's not going to affect the way the Earth rotates. And that would be the correct answer. To put a little bit of meat on that answer, we can look at the amount of energy that's stored in the magnetic field of the Earth and compare that to the amount of rotational energy that's present in the Earth as it's rotating. There are very handy-dandy little formulae for calculating that. For the magnetic field energy, the energy in the entire field, that's basically the volume of the field times this quantity b squared divided by 8 pi, where b is the magnetic field strength in Gauss units. And so if you put in reasonable numbers for the Earth, you put in a volume as a sphere that has a radius of 6,378 kilometers, 6,378 kilometers, turn the crank, the energy stored in the magnetic field of the Earth is about 10 to the 18 joules. The energy present in the rotation of the Earth is from a different formula, It's E equals 1/2 I omega squared, where I is the moment of inertia of the Earth, and omega is the angular velocity in steradians per second. Well, we can calculate both of those. I, the moment of inertia, is measured very precisely by satellites. So we know that number exactly. And we also know the Earth rotates once every 24 hours, which means that it rotates 2 pi divided by 24 hours in terms of an angular speed. And so when we put those numbers in, we get an energy of about close to 3 by 10 to the 29 joules. So comparing those two, the energy in the magnetic field is about 10 billion times weaker than or less than the rotational energy of the Earth. So to argue that somehow the Earth's magnetic polarity flipping is going to somehow influence the way the Earth rotates is like saying that a mosquito that kicks a bowling ball is somehow going to influence the way the bowling ball then moves, which is completely implausible. So that's sort of the definitive answer to, why it is that the flipping of the Earth's magnetic field, which will happen because it has happened in the past, will have absolutely no effect on the rotation of the Earth whatsoever. So there you go. That's sort of the bottom line on that. Now, you're going to go off probably and do some Google searching, which is what I do sometimes. Well, I do quite a bit of it, actually. And you're going to find articles that confuse reversals and excursions. But you now understand that there is a big difference between the two. Reversals happen all the time, but only the most excursions happen all the time, but it's only the most extreme excursions that actually lead to reversals. For the case of the excursion that we had in 42,000 years ago, you can look up articles on it, and University of Melbourne says, when Earth's magnetic field flipped, and they're talking about this event 42,000 years ago. Well, it didn't flip. It was an excursion. It just got weak, and then it grew back up. New Scientist, magnetic field flipping linked to extinctions. Not really. Again, they're using the word flipping and not excursions, and there are two different things that go on between those two. Excursions, the field will not go down to zero, so no harm, no foul. With reversals, the field will go down to zero, and then you could very well have some interesting effects. So anyway, this is sort of the layout of what you see if you do a Google search on reversals, excursions, and recent history. Finally, I'd like to remind you that we have some interesting to think about. There is going to be a reversal, a magnetic reversal in the future. It may not occur in 1815 years. It may take another 100,000 years for that excursion to really become so extreme that you wind up with a reversal. But we have some evidence of what's happened in the past because we've been able to track dozens, if not hundreds, of these magnetic reversals back through time. And we can see what happens, to speciation and life and other geophysical circumstances. First of all, is there going to be extinction of some species? No. There's no fossil evidence that shows that when you have a magnetic reversal, that anything unusual happens to the animal life on the surface of the Earth. Power grid problems. Well, if we have power grids in that future age, there probably will be problems because the way that the Earth's magnetic field is distributed around the Earth is going to be different. It'll be opposite to what it currently is. And so that means that some currents will flow backwards. They might flow in circular motion or any other kinds of things. So it could be very complicated, which means that your electric power grid is now going to be assaulted by all kinds of very strange current effects in the ground. Aurora will be seen in unusual geographic locations, very likely during the transition from the one polarity state to the other. You're going to go through this state where things are very irregular and lumpy in terms of magnetic field strength. And around those lumps, you're going to have aurora. And around places that are not near those lumps, you're not going to have aurora at all. So it's going to look very different than it looks right now, where the aurora are confined only to the Arctic and Antarctic. Disoriented animal navigation, very likely. So that's something that we could think about. That animals use the direction of the magnetic field of the Earth in their hemisphere to decide which direction to travel in terms of latitude, to find food or to find hunting grounds, stuff like that. Human health risks from ultraviolet exposure. There might be some risks to that. There will certainly be risks during jet flights at high altitude because you will not have such a strong magnetic field to shield some of the cosmic ray particles that enter the high altitudes. So you might be more exposed to radiation than you would otherwise. So that's a problem. Day-to-day life impacted? Not at all. I mean, you're down here under a very thick atmosphere that shields you from just about everything, and we don't rely on magnetic navigation like we used to. So you probably won't even notice anything is going on at all for the most part, unless you happen to look up at night and you might see aurora in some implausible places around the equator and other areas. And then finally, mass hysteria. Will a magnetic reversal cause mass hysteria? Probably not, because this is the classic boiling frog effect. If you put a frog in water and turn the temperature of the water up 1 degree, every hour, you can effectively boil the frog to death, because the change in the temperature will be so slight the frog won't perceive it as being a hazard. And that's what's going to happen to us as we approach one of these events. The event time maybe is only about 100 to 200 years. That's how quickly these reversals can happen. But over that time, we'll have plenty of years to adapt to the subtle changes that are going to be occurring. And so we might not even notice it, even if we're paying attention to it. So that's my presentation tonight. Next time, we're going to look at solar superflares. Is there one in our future? And the answer is, you betcha. So I think at this point, Sharon, you have some additional slides you want to present. I'll